Okay, looking at your review for your test coming up, I started off with 10 definitions, and I thought originally, well, I'm just going to skip those and let him look those up on his own or find them in the teacher's notes. But I decided to go ahead and kind of run through this, and I'll try to go through it quickly, but at the same time, I don't want to go through it so fast that you don't understand what I'm talking about. All right, the very first one, oh, and I didn't even write it all out. It's a reference, here, let me write it out. It's a reference angle. Definitely got into too much of a hurry there. The reference angle, okay, every angle has every non-quadrantal angle. You know, we don't look at the angles that are 90 or multiples of 90 or pi over 2 or multiples of pi over 2. But every other angle has a reference angle. If it's acute, it's itself. You know, the angle itself is its own reference angle. It is a positive acute angle that you can make from the terminal side of the angle. Now, that's if the angle is in standard position. Remember what standard position is. Standard position, kind of like what I've got drawn here. The vertex is at the origin. The initial ray is in the positive direction of the horizontal axis. And in this case, this thing opens up counterclockwise to this ray here, which is its terminal side or terminal ray, initial side or initial ray. But this is not your reference angle, because it's the angle that's formed with this terminal side and the x-axis. So this would be right here. And as you can see, if this is 160, that means that this guy here is 20 degrees. So the reference angle for a 160 degree angle is 20 degrees. There's your example, because they also asked for an example. Now remember that if you have the angle in the first quadrant, it's acute angle. In the second quadrant, the relationship with the trig values for the reference angle is 180 minus that angle. In the third quadrant, it's 180 degrees plus that angle, that reference angle. And in the fourth quadrant, it's 360 degrees minus that angle. We'll come into play with that a little bit. Coterminal angles. The name gives it away, co-terminal. They have the same terminal side. Angles, when in standard position, have the same terminal sides. Here's a couple of examples. Like I have this 160 degree angle right here. This terminal side. What other angles are coterminal? Well, I've got negative 200 is one, because instead of going counterclockwise 160, I go clockwise 180 plus 20, 200 degrees. So that would be negative 200. Or if I wanted to get a little fancy, I've also got 520 degrees. You say, well, how'd you get that? Anytime you add a multiple, or like here I subtracted 360, if I add 360 or a multiple of 360, I get a coterminal angle. So 520 would be like all the way around and then to here. And that would be coterminal. It would have the same terminal side. Are these angles the same angles? No. But they do have something in common, and that is that terminal side, because we know that we can find the sines and the cosines and all that where the terminal side intersects the unit circle. The cosine's the x value, the sine's the y value where it intersects. So coterminal angles, reference angles, very important. They give you an angle, you should be able to find its reference angle. They give you an angle that you should be able to find at least one positive and one negative coterminal angles by either adding or subtracting 360 degrees or 2 pi radians. I just did them with degrees here because I had this drawing up here. Speaking of radians, radian is a unit of angle measure. Just like feet is a unit of linear measure, a radian is one way that we can measure angles. And it is equal, are you ready, to the central angle. Remember, that means vertex at the center. I put this one in standard form here, whose intercepted arc is equal in length to the length of the radius. Now, I don't know if you can see it very well, but the intercepted arc here is here in green. The length of the radius is from here to here. I tried to make that purple, but I don't know if you can see it very well. Maybe you can now. If this length equals this length, then the measure of theta is 1 radian. As it turns out, I'm not sure if it's 57.1, 57.2. I think it's about 57.2 degrees. So that's what a radian is. Now, if they ask you for an example of a radian, we can say that 90 degrees or 180 degrees is equal to pi radians. But I went ahead and listed it this way. The degree is probably a little bit more universal measure, at least here in high school, for measuring angles. It's a unit of angle measure, so that all the way around, at the central angle all the way around, it's 1/360th of a full rotation or full revolution. So if I go all the way around, it's 360 degrees. So it would be 1/360th of it. Now I can't even draw it that small. That's probably too big. It's a pretty small angle. And we know, for example, that pi over 4 radians is 45 degrees. So that's another way that we measure angles. With radians, with degrees. There's even a third unit called gradients, but I don't think you're going to worry about seeing that for a while, if ever. An inverse function. Now this is very general. An inverse function, in layman terms, is a function that reverses another function. Like if I open the window and then I close the window, those two functions are inverses of one another, because you end up, when you do both, right back where you started. So in this case, more mathematical, is that it says a function f has an inverse function f inverse, which I get with a little -1 up there like an exponent, such that if you compose f of f inverse of x is equal to f inverse of f of x in either order, that you get right back to x. You get right back to the identity, whatever you plugged in. So you studied this way back, maybe even as far back as Algebra 1. Here's a couple of simple functions that are inverses. You can see if I take the number 10, I plug 10 in. 10 plus 5, 15. I plug 15 in here. 15 minus 5, right back to 10. These two functions will undo or reverse one another. But you're studying trigonometry, so what are we doing with inverse functions? Well, we have the sine of a function, we have the inverse sine of a function. We have the cosine of a function, we have the inverse cosine. Tangent, inverse tangent. All right? Reciprocal trigonometry, the best I can figure out is he's talking about the reciprocal identities. And now one trig function is the reciprocal of another trig function, but you just can't pick whichever ones you want. These are the guys right here. Cotangent and tangent are reciprocals of one another. Secant and cosine are reciprocals of one another. Cosecant and sine are reciprocals of one another. And I would put these to memory, because you should know your unit circle and all the sines and cosines. So if they ask you to find any of these, you can find them by plugging in, because you know sines and cosines. And of course tangent is sine of theta divided by cosine of theta. So you can find them all. Now when you started doing some graphing on these last couple of assignments, you started talking a little bit about vertical and phase shifts. All right? Vertical and phase shifts, they're just translations. There are different kinds of transformations in graphing. There are rotations where you spin it, reflections where you flip it, stretching or dilation, stretching or shrinking, vertically or horizontally, right? And there's also shifting, and that's what this is. A translation is when you shift your graph, right, left, or upward, downward, or a combination of both. So I wrote down this example, and I put the A, the B, the H, and the K there. Those would represent numbers. Your variable is theta. And I just picked cosine. I could have used any of them. But in this case, you can see what the phase shift is going to be for this graph based on what this value is right here. Now notice it's minus h. So if that was like minus 5, it would go 5 to the right. Plus 5 would be minus and negative 5. It would go 5 to the left. And the k is the vertical shift. The k out here. And it looks just like it is. If it's a positive number, it goes upward that many units, k units. If it's minus k, it goes down k units. Vertical and phase shifts, translations. Amplitude. Amplitude, I know how to explain how to find it right away, and I've kind of explained that to you in the past, but it's the height of the average value of the function to either its max or to its min. You can see the symmetry in some ways here with the x-axis. Now it's not symmetric to the x-axis, but you can see that it rises above, it lowers below in these same little loops of the wave. Well, the distance above here, up here at 1, that's its maximum, but down here it's 1. Or down here it's -1, but that's a distance of 1. So this is kind of like its mean value here at 0. So the amplitude for the sine wave is 1, because you would find it by taking the maximum value, subtract the minimum value, and divide by 2. That's the formula that you're going to need to remember. And only sine and cosine have amplitude. The other 4 trig functions do not. Sinusoid, and I think I pronounced that right. A sinusoid is a curve that has the form of a sine wave, like the one I have here. That is the sine wave. If I graph this guy out, This may shrink the period and it may stretch it out vertically because you're multiplying by 3, affect the period here, excuse me, the amplitude here, the period here. The period would be pi, 2 pi divided by pi, and we haven't talked about the period, and the amplitude would be 3 because the amplitude is the absolute value of whatever this constant is in front of the sine or cosine function. So that would be an example by graph data of what they call a sinusoid. It has that basic sine wave. And the period. The period, because of the functions that we're dealing with, all 6 functions are periodic is what they're called. Or sometimes they call them cyclic, but periodic is a better description. It is the distance on kind of like the x-axis that's required, or the theta axis, that's required for the function to complete one full cycle, one full period. So like, for example, the sine here, you see where it hits the x-axis here? At 0, 0, it goes up, it comes back down, and then it starts to rise up again, but it hits right here. This distance from 0, 0 to, and this is, let's say that's pi over 2, so that's pi, 3 pi over 2, 2 pi. This distance here, 2 pi, would be the period of the sine wave. It's also the period of the cosine wave. Okay, remember, for 4 of the trig functions, sine, cosine, secant, cosecant, the period is 2 pi. For tangent and for cotangent, the period is pi. It repeats itself every pi. So that's kind of a description of your vocabulary terms, and we'll start some of the other problems here on the coterminals. So make sure that you have a pretty good feel for the understanding so that when you see these terms used in the directions, you'll know exactly what's going on.